live. Thank you very much, Yana.
Thank you.
The next speaker is from Canada. We haven't talked much yet, but lately, but here we are talking via South Africa. Many familiar faces, and also, yes, Dilling from TRIUMF, talking about precision experiments using radioactive beams. Go ahead, Jens, and please allow some time for questions. But since you are the last speaker in the session, I guess we can relax and have a bunch of questions at the end. Go ahead.
All right, super. Thank you very much. It's a pleasure to be here. I'm very excited to be a part of this TASTE this year, an exciting conference series for students and researchers around the world, and I'm happy to talk to you. So Nico asked me to give you a little bit of an overview of mass measurements and precision experiments using radioactive beams, and that's what I will try to do. And this is the last talk of the day, so thanks for all of you who stuck around and learn what we have been doing in Canada. So let's jump into that. I have my pointer here. Why do we do atomic mass measurements? Well, atomic mass measurements via the binding energy encapsulates all interactions and reveals a lot of information that we are after in nuclear physics. The binding energy can be extracted from the mass if you know the constituents that are included, the neutrons, the protons, and the electrons. And it builds up the entire chart of isotopes. But we can extract even more information if you look, for instance, for the binding energy for nuclei. So you build up a picture and you see the scale here in the bottom right, where you get detailed fingerprints the interactions that is revealed in the binding energy. You can play all kinds of tricks. You can look, for instance, for the neutron separation energy. And you, all of a sudden, all kinds of features appear on the chart and familiar patterns emerges. And you can go even a step further and look for derivatives. Here we're looking at the second derivative. Where you take a ratio between binding energies of nuclei that are 2 removed, so you get the second derivative, and you get even more features building up, and these are very familiar features, and this is what we want to extract. And again, all of this comes from having access to mass measurements. So you can look for the evolution of nuclear shells, and what kind of precision you need in the mass measurements is governed by the questions that you ask. So if you want to learn something about those patterns, the typical precision that you need in a mass measurement, and I express it as relative mass uncertainty as a function of mass, is something like 10 to the minus 6 or 10 to the minus 5. At that level, you already see features appear. For very special features in nuclear structure, like halos and skins, you need to up your game and improve your precision up to 10 to minus 7. Similarly, if you're looking for nuclear astrophysics, nuclear synthesis, here specifically for the R process, somewhere between 10 to minus 6 and 10 to minus 7 is needed. And for fundamental symmetries, you need to even go further up. So here I've depicted 10 to minus 8 as the requirement. And for very special cases, let's say in neutrino physics, you need to improve that even by something like 1 or 2 orders of magnitude, 10 to minus 9 relative uncertainty. And here comes the reality check. What is currently known, this is the mass accuracy as a function of color. You see the uncertainty depicted here. And as you would expect, the closer you are to the value of stability, the better the uncertainty is. So this is one then less than 1 unit here. And the further you go out, it gets harder and harder, and your precision drops down. So how do we actually do those mass measurements, and what are the tools of the trade? Well, the trick is to use ions. You remove at least 1 electron from the isotope that is being produced. And now you can open the toolbox of electromagnetic interactions for interacting with the charged particle. And you have all your forces well understood, and you can use that to apply to any radioactive ion and isolate it from contaminants that are being co-produced in the production mechanism, and you can manipulate it before it decays. And that allows you to carry out the measurements that you're interested in. Excuse me. And typically for experiments at radioactive beams, we have 3 primary types of ions that we use to carry out those experiments. The first one is an electrostatic device. Here we use a multi-reflection electrostatic device. And to give you a scale, this is about 50 centimeters. And it consists of a pair of electrostatic mirrors. It's used for mass measurements. It's used for beam purification, or you can use it for decay spectroscopy. Our main tool is a penning trap. The scale here is a lot smaller. So here you see 1 centimeter is covering a large fraction of that device typically. It uses magnetic and electrostatic fields. And the applications are for mass measurements, for decay spectroscopy, also for beam purification, and for charge breeding. That's a special case, and I will come to that in a second. Or you can use what is called a Paul trap, that is making use of oscillating electric fields used for beam preparation, beam purification, and for decay spectroscopy. So you have the full flavor, from completely electrostatic to magnetic and electrostatic to electrodynamic with oscillating field. Where are those traps used at radioactive beam facility? Well, it all started at CERN, where many years ago, first traps were deployed with radioactive beams, also with antimatter beams. But now it has spread all over the world. We heard from Jyväskylä already just now, but essentially every radioactive beam facility around the world either has ion traps at their disposal or developing ion traps for use for beam purification or for measurements. It's a very powerful tool, and the popularity is rising. Everyone wants to have it. And I think there are even plans to build one at IFEMPA. So I will focus for now on the trap that I built many, many years ago at the ISAC facility at TRIUMF, and the system is called Titan. So let's see where we get our radioactive beam from. We use TRIUMF, and TRIUMF is Canada's Particle Accelerator Center, beautiful location in Vancouver, British Columbia, on the west coast of North American continent. Here you see the university campus, and here at the bottom is the facility, the accelerator facility. TRIUMF is owned and operated by 21 Canadian universities, so it's a consortium to enable world-class research in a variety of fields. It's where teams come together for things that are typically too big or too complicated to be done at a university. And it's a lot of students and postdocs receive their training, making use of the unique facilities that we have at TRIUMF. It's a very powerful facility, and I'm excited to tell you what we've been doing there. The overall science program that we have at TRIUMF is focusing on the inner space and the outer space. And everything is centered around accelerators, detectors, and data science. And we fill the circle here with cosmology and dark matter, moving over to particle physics, nuclear physics, which is part of what we're talking about today. But we also have molecular material sciences, nuclear medicine, and we use the powerful accelerators also to understand electronics and radiations, and of course, closing the loop with nuclear astrophysics. So these are the topics of today's talk. All in all, we are happy to have the world's largest cyclotron. It's a very powerful machine. It's in operation for over 40 years, and it's delivering very powerful continuous proton beams of up to 500 MeV. And here's how we use them. The TRIUMF cyclotron delivers the continuous beam, comes out and goes into this facility here, which is called ISAC. 500 MeV protons strike a target, and spallation, fragmentation, and fission reaction takes place and synthesize new isotopes. What I've depicted here in this little graphic is, of course, only spallation, but all three channels are open depending on what kind of target material you're using. The beam gets formed by ionization here in the target and electrostatic extraction out of the target and delivered to the first unit, which is a dipole mass separator. So here we separate in fairly coarse terms all the products that come out of the target stations here and deliver it as a low energy beam to the experimental station. Here for now I will focus on this unit, but all in all, we have 18 experimental stations at the ISAC experimental facilities. We have a low energy beam. We have a post-accelerated beam that goes up to 1.5 MeV per nucleon, or we can go even further with superconducting accelerators up to 16 MeV per nucleon. For now, I will just focus on the mass measurement unit, which is the experiment called Titan. So this is a fairly complex device, and it's making use of a number of those traps that I introduced earlier in combination with each other. From the left, the continuous ISAC beam of radioactive species is delivered to the first unit here, which is called a radio frequency quadrupole. And then it can be further delivered either downwards, injected in here and down again for laser spectroscopy, or upwards to the next unit, which is a so-called multi-reflection time-of-flight spectrometer, and then further and further, eventually to the penning trap where the mass measurement is carried out. Well, let's start slow. I'm going to start with the RFQ. So an RFQ is a radio frequency in quadrupole, and it allows transverse confinement. So here you look basically along the axis of where the ions are injected, and you see these four half circles, and they are an opposite RF polarity. And essentially the beam comes in and it's charged particles, and they bounce in between those shells here, which is depicted here as a saddle potential on the left side, confining the particles inside that tunnel, so they are not interacting with the walls and get lost. And on top of that, we have axial segmentation. So these rods that go down into your screen are segmented longitudinally, and that allows you to apply additional trapping potentials. And in combination with buffer gas, it allows you to store particles inside this environment, overlaid with the buffer gas that leads to interactions and eventually to cooling and accumulation at the very bottom here. So now you have the continuous beam converted into a bunch of ions that are accumulated here in the potential minimum. and they are slowed down and can be extracted as a pulse beam. That's a powerful first step to convert a radioactive continuous beam into a bunch beam for further processing. So the next step that we want to do is take it into the mass measurement panning trap. Let's take a look at that. We start with a magnetic field, and the ions start to spin around the axis. You have a strong magnetic field, they start to spin around, and you overlay that magnetic field with an electrostatic potential, and you trap them on axis. And the resulting motion is trapping in 3 dimensions. The charged particles no longer can escape and are trapped inside this environment here. And you have a well-defined, well-understood motion that only depends on the cyclotron frequency. And if you want to do precision measurements, counting frequencies is the best you can do. You just need to count, and you need to know how long a second is, and you have reduced your entire measurement to just counting. So very, very powerful. Now, if you're dealing with radioactive isotopes, you have to be able to do all of this very, very fast. And we managed to do that for isotopes as short-lived as 9 milliseconds in the form of lithium-11. So the other thing that is very, very powerful besides counting frequencies is that the motion is extremely well understood. And that's true in theory and in practice. We've converted a nuclear physics measurement to an atomic physics measurement, because the motion behaves exactly the same, whether this is a stable particle or a radioactive particle. And that allows you to carry out very, very detailed precision, accuracy, systematic tests. You understand your system extremely well, and that's a prerequisite for being able to make those measurements with isotopes where you no longer know how heavy they are. So you can describe your system, you know exactly what kind of frequency you're measuring, and you have total control over your systematics. So very, very powerful. So, and then you can apply that. The first example that I have here is testing the CKM matrix, the quark-mixing matrix. And I think there are some more talks on that topic later on in this week, where we want to look how the weak eigenstates and the mass eigenstates are mixing together. And in particular, we're interested in the unitarity of this matrix here, where the top row is the most stringent test. And in the top row, we have contribution from the U and D quarks, which of course make up the neutrons and protons in the nucleus. What we are looking at are super loud beta emitters, where neutrons and protons are converted into each other, and describe exactly this mixing. And the value of interest here is the so-called FT value that contains experimental information about the so-called Q value, or the mass, the half-life, and the branching ratio. And the theory says that this VUD can be extracted from a whole series of FT values from the supraloud beta decays. And it predicts this to be constant once the appropriate corrections are applied. Now we want to focus on magnesium-22, which, as you see, has fairly large error bars, and we try to boil that down to get a better understanding of that. So magnesium-22 decays to sodium-22, and we are interested in extracting this Q value here, and we are doing that by determining the mass. And this is how the mass plot eventually looks, by measuring this frequency here. And I will go into a little bit more details in a second, but I want you to look at those numbers here. So we can determine Q values on the level of 200 eV. And if you go a little bit further, we even boil that down to 160 eV. So very high precision, eV, hundreds of eV type precisions for nuclear physics measurements. So where is that precision coming from? What is necessary? Well, let's take a look. This delta M over M in our kind of measurement depends on a number of factors here. And you see here a Q, a B, a T, and an N. So N is, of course, the statistics. It goes with the square root. Here we have limits from production. You cannot run that system for weeks without end, because then it becomes really difficult to understand your systematics and your stability of the systems. The RF is the measurement time. How long can you actually keep a single charged particle in that trap and expose it to the fields that allows you to count frequencies? The B is, of course, the magnetic field strength. You had a stronger magnet, you would be able to achieve higher frequencies, and higher frequencies corresponds to a higher position. But there's an additional handle that you have, and that is the charge state. So far, we've been talking about singly charged ions, atoms where one electron has been removed. So it turns out that is a big handle. If you convert this 1 from a charge state 1 to, let's say, 10 or 50, that's the kind of precision you might be able to gain. So how can you get to a charge state that is more than just 1 that comes from the radioactive beam ion source? You have to do further manipulation. Let's see how this can be done. We do that in a device called Electron Beam ion trap, and it allows you to do charge breeding. You have a system here where that consists essentially out of a penning trap with a strong magnetic field, but you have additional features here. You have a cathode that shoots an electron beam right into the center of this trap and eventually collects it here. So it's a continuous beam of electrons that go through this trapping environment. And now you start filling this trap with your singly charged ions. They come from the buncher, they come as a bunch, well-defined quantities in well-defined energy packets. They get trapped inside here and are exposed to this electron beam. And now you have electron beam ionization. So it's bombarding these singly charged ions with a whole bunch of electrons that have higher energies than the binding energy that they are attached to the atom. They are converted to higher charged isotopes, highly charged ions that get extracted and sent on the way. And here you get a time-of-flight spectrum using a device, Bradbury-Nielsen gate. You can very quickly flip that on and off and let part of the beam go through, and you see that the very charged states are populated. And you can make use of that to increase your precision to tackle other scientific problems. So here we're looking at cadmium isotopes near mass 130. And with this increased charge state, so we have a charge state of 13 plus, you can actually resolve ground state and isomeric state. Here is the plot of 2 neutron separation energy. Color band here tells you how well those values were known previously. And then these are the measurements that we carried out and published a few years back. Let's look a little bit further for a science case for nuclear shells. Again, we are looking at this second derivative of the binding energy here. And the nuclear shells, as we have heard, might evolve away from stability. And the typical way to look at that is with 2 neutron separation energies. Here again, we're looking at indium and cadmium cases, and let's see what we can extract from there. Unfortunately, in reality, if you want to look for a beam in the mass 130 region, they are plagued by co-produced beam from the radioactive beam facility. Various reaction channels are open in the beam production, and you get all kinds of co-produced isotopes along with the isotopes that you're really interested in. So what can you do? You get your beam from ISAC, from the radioactive beam facility, and you want to bring it somewhere here, where is a single ion in the trap. So maybe you have to do something else. Maybe you have to tackle the problem at the start. And this is where this device comes in. So we're going to use what is called the multi-reflection time-of-flight mass spectrometer, and it's based on simple kinematic. You have an ion source and you fly 3 ions with different mass over a period of length, and they will arrive, depending on their mass, at different times. And the lighter they are, they will come faster, and it's just fact if they have the same kinetic energy to start with, their velocity will be different. So now we play a trick, and we put 2 electrostatic mirrors in between this flight path. Let the ions not just go through here, but let them bounce back and forth many, many times and increase the overall length that the ions have to fly. And your separation here will get larger, and you will get an increased precision of how you can resolve these ions that come from here. So this is what we did here. We did measurements of these indium isotopes, and we actually managed to have 3 new records achieved during that measurement. So the first measurement that we did was looking at an isomer. So we had an isomer of 5 milliseconds, and that's the shortest species that we've measured so far at the Titan facility. And we did that by coupling a little trap in front of this electrostatic mirror and held the ions in that trap before we released it in here. And with that, you could vary what kind of half-lives you can measure, because the ions have to be stored here. Some will decay, some will survive, and you get different patterns. That's reflected here with the added storage time. The second record that we did, we could look for first isomer separation using this retrapping technique. We did separation, and then we bounced it back into the trap, stored it, and released it again. And that allowed us to separate a low spin and a high spin, which is reflected in 2 different masses. Higher spin has a higher mass, higher energy, and hence a higher mass, and would be arriving at a later time. And the third was we could actually identify an unknown isomer that appeared here at the shoulder, and this is something that we're still trying to figure out, but that hasn't been seen so far, and we could resolve that. So this is a forthcoming publication by our postdoc, Chris Izzo. So let me just summarize. Ion traps are powerful tools, prepare beams from radioactive beam experiments, carry out experiments for nuclear structure, and to probe fundamental symmetries in nature. And to use them in combination to gain precision, to reduce background and gain signal to noise. There's more to learn and explore, improve efficiencies, reduce background, storage times. Great training ground for students and postdocs. And if you want to learn more, please come and talk to me. Before I hand over to our chairwoman for questions, I would like to thank you for paying attention, and the team of students and postdocs and collaborators from Canada and around the world that participate in the Titan experiments. Thank you very much.
Thank you very much, Jens. We have some questions in the chat, but we are happy to take some more questions from the audience. So there is one from Mark Griffith. Hello, Jens, really enjoying your talk. I would just like to ask for a rough explanation of the desired percentage uncertainty in atomic masses for the different fields.
I'm not sure I got that. Okay, let's see. Okay. So I guess this goes back to the question of the motivation, what kind of precision you need for the various fields. And it is essentially coupled to the scientific questions you're trying to answer. For the example that I gave in testing the CKM matrix, here you need higher precision because the theoretical predictions are of very high quality, and the Q value goes into the formula with a fairly high power, to the power of 5. For nuclear structure, where you already see features at lower resolution, 10 to minus 6 or 10 to minus 7, is when these patterns appear. And I will just go back to my initial slides where you can take a look at that. Something like this. Let me share that again. So some of these features are already visible at lower resolution, and you can already extract information from that. And then the highest resolution that you need is for neutrino measurements, where it is coupled to the mass of the neutrino that you're aiming at. So for instance, for capturing, they're aiming at a neutrino mass determination of EV or milli-EV. And so you need to determine the endpoint of that decay with fairly high precision, ideally with the same kind of resolution. So you know where to look for the deviation from the expected curve. Right? Hope that answered that.
Yeah, thank you. There is another question from Vivek Dattar. Typically, how many ions are needed for 1 in 10 to the 9 precision in mass?
Good question. So we actually do the measurement with 1 ion at a time. And then it's just the various factors that come into play. So how long you can store the single ion and expose it to the RF, and then your statistical factor. It's about a few hundred ions that you need. For 10 to minus 9, it's probably around 1,000 ions. For 10 to minus 6, you will get away with under 100 ions.
Thank you. Any other question? If not, I see the weather is very nice in Vancouver. We can all.
Yeah, that's unfortunately not real.
I hear the rain. Okay. Thank you very much, Jens.
Well, thanks for having me. This is a great conference, and I'm happy to be part of it. And
yes.
Again, to all the students and postdocs out there, if you want to learn more, please reach out to me. I'm happy to connect.
Let's give a round of applause to Jens and to all the speakers of the session and of the day. And thank you very much for this event, Nico. And I'm sure the following days will be a great success. Thank you very much and have a great day or evening.
Thank you so much, Corina. A round of applause for Corina as well. Thank you for being there. So I want just to make a few announcements here. Let me just quickly thank you so much, Jens, for such a nice presentation. I want to say just a couple of things.